Well, thanks so much for the introduction. Who wrote those? It's a great pleasure for Eric and I to be able to represent our colleagues at ALS to share with you guys the small angle scattering capabilities at the advanced light source. Let me start with the overview of the ALS Lawrence Berkeley Lab, which is located in Berkeley, California, right adjacent to the University of California Berkeley campus, and overlooks the San Francisco Bay. So basically, the dome building that you see on the screen here is where ALS is located. This is actually the birthplace of the big facility and big team science, which pioneered by the founder of Berkeley Lab, Ernest Lawrence. And this dome building that you see here is actually the home of the 184-inch cyclotron that made him famous in the 1940s. So this dome building is actually designed by an architect named Arthur Brown Jr., who is also the designer of the San Francisco City Hall, the Coy Tower, and the Opera House, etc. So this is really a historical site that the modern ALS is built upon. So the modern ALS is actually constructed in 1993. So we basically have a 1.9 GeV ring in a about less than 200 meter size ring. So it's on the small side of the synchrotrons. Therefore, our peak brightness is in the soft and tender X-ray range. So that's our real strength. So far we have about 200 ALS staff, with about 50 of them are practicing materials, physics, and chemistry as beamline scientists. So over the years, so ALS now has about 40 beamlines total. We serve more than 2,000 users a year with about 5,000 total operation hours. And so being the soft X-ray smaller ring, our really strength is on the soft X-ray wavelengths. And being the synchrotron that is almost 30 years old, actually ALS is due for upgrade. So I'll mention that briefly at the end. So to access ALS, we usually take the general user proposals. This is probably different from some other facilities. We have two cycles, the spring cycle and fall cycle. The proposal submission is the first Wednesday of March and September. And in the meantime, we have this rapid access mode. So if you have some urgent stuff you want to look at, or you have the industry proposals, you can submit anytime. All this information can be found at ALS Hub and ALS website. Here's a closer look of the beamlines at ALS. We have 40 total. Its covers range from IR to hard X-ray diffraction. The whole spectrum of X-ray technologies range from microscopy, spectroscopy, diffraction, and today we're here to talk about scattering. So all the beamlines circled here actually have some of the scattering capabilities, including the Sachs-Wax beamline, the Scheible's beamline, which is BioSax, which is actually one of the first Sachs beamlines ALS, and as well as some scattering beamlines using the soft and tender X-ray range. So what I'm going to focus on today will be this beamlines, which is clustered under the ALS scattering program. The ALS scattering program is led by Sujoy Roy. That has been formed about 3 years ago, where we cover from the soft, tender to hard X-ray range scattering capabilities that covers the K edges of low Z elements, transition metal L edges, all the way to sulfur, potassium edges for the tender range. Sujoy and Sophie here is actually working on the coherent X-ray scattering using the soft X-ray range and at beamline 7 and 12. Myself and David Kilcombe is working on the resin soft X-ray scattering beamline 11. And Gregory Su, a recent addition to the team, actually is working on the development project on the tender X-ray scattering, as well as Cheng and Eric is in charge of the beamline 723, which is a hard X-ray Sachs and Wax. And actually, the Sachs-Wax beamline at the soft X-ray facility is actually the most important start of the whole scattering program. In 2006, in ALS, there was only one small angle scattering setup, that is the Scheible's, that is focused on the biological scattering. There was no material science scattering program at ALS. Back then, the management made a strategic decision, decided to build a Sachs wax beamline at ALS. They actually invited Dr. Wang from the ESR back then, who led the development of the most productive Sachs wax beamline worldwide. And he was here able to help us to build the 733. Als Caching was the first beamline scientist there. And since then, the program has took off and really become the anchor of the material science research community in the Berkeley and LBL, and actually become the start of the whole scattering program here. I would say the soft and tender. For the coherent scattering, that's coming from a different direction from condensed matter physics direction, but eventually it emerges as strategically we're moving towards coherence. But without the success of the 733, the soft actually scattering and tender would not be at the stage now. All right, so with that, let's start with this more details about the 733. I will switch the gear to Eric Schaible, so he will give us an introduction of the 733 Sachs wax beamline. I will stop share. Eric, you can start.
All right, can you see my screen?
Yes.
Good. Thanks very much, Cheng. I'm going to talk about hard X-ray scattering facilities at the ALS. And as Cheng mentioned, we are primarily a soft X-ray source, but we do have some hard X-ray scattering capabilities. Those are the BioSax beamline that we have and 733, and I'll talk about both of those. Let me back up just a little and give a little background context here. This is going to this mode. Great. So coordination between light sources is very common and collaboration is very common. Many of our users go to multiple facilities and we have working groups to share knowledge between facilities. This seminar is an example of that kind of collaboration. The APS is going to have a dark period for the upgrade to APSU, and the ALS is happy to help provide a place for APS users to go to continue their research during that time. And similarly, the ALS is going to be upgrading on a staggered schedule, and we're going to have a dark period for our transition to ALSU. And so we'll probably be sending our users to APS. I'm going to start with not my own beamline, but the BioSax beamline. This is beamline 1231, also known as Sibbles, and this is a protein Sax beamline. They have high throughput protein Sax capabilities, so it's all robotically changed. You just send in a 96 well plate to them. They crank that out in 90 minutes. They also have purification coupled or SEC Sax capabilities. Similarly, you just ship the samples to them and they run it off. They will do all the data collection and processing for you. This is kind of a little flow chart for how you get access to their beamline. But the important thing is down at the bottom. You basically ship your plates to them. They collect the data. They process the data. They send you the data. They also have a very nice and very clear website for users who want to access their facilities. You can see here they have nice little buttons for requesting a mail-in account, registering with the ALS, submitting your proposal, booking your mail-in slot, and then good instructions for how to prepare your samples and ship them. So if you are interested in using their facilities, here are contacts, and you'll want to go to the Sibbles website listed here at bl1231.als.lbl.gov. I'm going to turn now to talking more about my own beamline. I'm one of the scientists. The other scientist is Cheng Zhu. Let me talk about just kind of again, the bigger picture here, which is that where the APS has many hard X-ray scattering beamlines that are specialized in many cases by technique or science area, the ALS has fewer hard X-ray scattering beamlines. And so we have comparatively less specialization. So if you have BioSax, thank you. For BioSax, that goes to Sibbles. Pretty much everything else for hard X-ray scattering goes to 733. So 733 has to be very flexible in order to accommodate a wide range of users. We're flexible in our geometries that we run. transmission sacks, wax, G-sacks, G-wax. We're flexible in the sample types, thin films, solutions, bulk samples of any material that our X-rays can penetrate. We do static measurements, in situ measurements, time-resolved measurements, a fair number of in situ experiments. And the science areas are similarly very diverse. A lot of them are focused on energy portfolio. So we do a lot of photovoltaics, batteries, fuel cells. We do a lot of polymer and soft matter work, MOFs, COFs, 2D materials. My own research focuses more on biomaterials, and Cheng has a heavy emphasis on liquid crystals. We are totally non-discriminatory about science areas. We have a lot of different science across material science, physics, chemistry, and biology, where again, that biology is not standardized protein sacks, other types of biology. We run in a couple different operating modes. So we used to almost always just have users collect their data in person. Then of course, COVID came along. We still do collection in person, and that's appropriate for any sort of measurements of any difficulty, static samples, all the way up to the most difficult in situ experiments. But we also now offer remote capabilities of two kinds. One where the user ships samples and then they collect from their home lab, so they log into our computers. And that's appropriate for measurements where the samples change not very often, or where the user can change them remotely by stage movement or robot. So the point being, it's not cases where the beamline scientist would have to change the sample individually every 10, 20 minutes. We also will sometimes run user samples where the beamline scientists will collect all the data. And that's okay in situations where all the measurements can be automated or semi-automated in large batches that will run for many hours. And we'll run in any of those operating modes. Let's take a look at the hardware and start with beamline technical specifications. The main things that you will want to be aware of is that the ALS hard X-ray scattering beamline can't duplicate all of the capabilities of all the diverse APS beamlines. So for example, we run at an operating energy of 10 keV, and that's worth noting. So that if your samples are particularly dense or particularly thick, so that you typically require an energy of 15 keV or more, then 733 is not going to be able to serve your needs, and you want to go elsewhere. Also note the Q range. We can't duplicate, for example, the Q range of Janilowski's beamline. If you need to see sizes greater than 150 nanometers, we also can't do that. But within those constraints, we're happy to run any sorts of samples. The ALS 733 end station is very similar to APS 12IDB. So users of that beamline will find the equipment very familiar. The motorized vacuum tube and motorized stand were in fact designed by APS engineer Oliver Schmidt and APS beamline scientist Byung-Du Lee. We're very happy to take this opportunity before an APS audience to give them full credit and thank them once again for sharing their excellent design with us. Basically the detector sits in the vacuum tube on rails, and it makes sample to detector distance changes very easy. We can change from sacks to wax in under 5 minutes. The beam stays on the beam stop the whole time. It makes the process very easy. So that's great. And again, thanks to Oliver Schmidt and Byung-Du Lee. It's again, like I said, it's evidence of the collaboration and sharing that happens between these laboratories. We do a wide range, as I said, of in situ experiments. These are some of the stages that we have available at the beamline. A lot of them are temperature stages for heating capillaries or thin films or bulk samples. We also have capabilities for solvent annealing, DSC, a tensile stage. I do a lot of the tensile mechanical testing on biomaterials myself. And we recently just got this humidity controller and is setting up a stage to be able to do humidified experiments. We also have a lot of users who bring in their own custom stages that they've designed, and we're happy to provide assistance with that process. So if you are designing a custom stage, we're happy to have you send CAD models that we can integrate into our beamline models and give you feedback, or send you CAD models of our stage platforms so you can do your bracketology. But we find this very helpful in ensuring the success of experiments with custom design stages, is doing this kind of CAD interchange. We're happy to provide assistance with that. This is a partial list to the right of some of the custom stages that have run at 733, a wide variety of different process control equipment. Here's another capability that we offer at the beamline. This is a helium environment. It's kind of a just hacked together box, but it's been incredibly useful and productive. It's basically a helium environment that we use for wax and G-wax samples that scatter weakly. The point being, the box is filled with helium, so the beam goes through a path of helium instead of air, and it doesn't generate tons of air scattering that will noise up your data. So you get improved signal to noise with this environment. And here you see us installing a slot die printer because this system, this helium environment, is particularly useful. We do use it for static samples, but it's particularly useful for in situ experiments that don't do well in vacuum. So here we are installing a slot die printer. That box then gets sealed up, all the holes get sealed up with Kapton, and then we print, and we're able to watch the printed film dry and evolve with improved signal to noise. The beamline for many years has also had a Grazing Incidence automated data collection system. Samples get mailed to us in the shipping containers, and then they're put on the robot table and run in automated batches. And actually, though, demand for this system has actually decreased since we introduced the helium box, because users prefer the improved data quality in that helium box for their grazing incidence measurements, and that's not compatible with the robot arm. So I need to build a load lock on that helium box, and instead of doing that, I've started planning a new sort of modular roll-up vacuum chamber that will work with the robot and that will provide similar data quality to the helium box. So that's one sort of robot project that we have in development right now. Another one is this pipetting and mixing robot that we purchased that will enable in situ mixing and pipetting of chemical and biological solutions at the beamline. Hopefully in the future that will be also perhaps combined with autonomous data collection. And that's we're just starting the development of that now. That's kind of an overview of the hardware. Let's take a look at the software at 733. The ALS is unique in the extent to which it uses LabVIEW-based software. And one of the good things about LabVIEW is that it forces the development and use of graphical user interfaces. And I'm a big fan of graphical user interfaces. I think they improve the experience for the user. They give good feedback, provided that they're well designed. So there are a lot of benefits. This is an example of our beamline software, a typical window you would see. It's very easy to learn to use. To jog sample positions around, you just push buttons, right, left, up, down. To take an image, you just enter an exposure time in the appropriate field and push a button. So it's very easy to train users to use, and it makes for a good user experience. The set of things you can do with this software is automatically, it's not wide open and unlimited so that you hardly know where to start. It's automatically restricted to only valid actions. You don't have to remember and learn command words, or you don't have to worry about syntax errors. And in addition to having graphical controls, you typically have graphical indicators that give you lots of visual feedback that what you're doing is working. So again, I think that the graphical user interface makes for a very good user experience. We've also tried to automate a lot of the repetitive actions involved in data collection. So for example, on the left, you see we have automated scans. That's pretty standard at beamlines like this to scan the sample across the beam. You can bookmark different sample positions and go to those sample positions at any time with a push of a button, or use those bookmark positions in a script later on in the software. We also have automated tiling of images where you check a box, and then anytime you take an image, it will actually take two images and combine those to get rid of the horizontal gaps in the Pilatus detector images. We have automated grazing incidence alignment. You just push a button and it will align your sample parallel with the beam in 30 to 60 seconds. So that's fast. It works very well. We have automated exposure time selection. And this is actually one of the best pieces of automation that I've written. It's been very helpful. It again makes training easy for if users want to know what exposure time to use. They just push a button. It takes a very short, like 100 millisecond exposure, and then looks at that and says, come back an answer. You should take a 30-second exposure. That'll give you, lots of signal without saturating the detector. So it helps the user, and it also protects the detector. That's been very useful. That's also available for use in scripts later on. I have a little note here, automated rad damage, and this is something that I'm looking at trying to develop next. I'd like to put in a button that the user can push, and then it takes a series of images, 1 second images, 10-second images, and comes back to the user with a radiation dose limit. It says your scattering curves start changing at 60 seconds. You're getting radiation damage at 60 seconds. You should stay below that. And that would be very, very convenient. I'm looking at developing that next. I find automation like this benefits the user in multiple ways. It gives, again, a good user experience because it gets rid of repetitive, tedious tasks and frees up the user to focus on the science and what they're really there to do. It also makes measurements more reproducible and limits the opportunities for human error at 3 a.m. after you've been running all night. Now, graphical user interfaces like I said, are restrictive, but we do have flexibility in that we have an instruction queue that you can build. So you can script out arbitrary sequences of individual actions, of motor movements, of movements to particular sample positions, detector steps, temperature changes, grazing incidence alignments, timings, and you can build a whole series of instructions and execute them. You can also script out multi-dimensional scans. So examples of these would be if you want to go from 30C to 100C in 10C steps, and at each temperature, then go to any one of 10 sample positions and image each sample at each temperature. Another good example would be if you've marked off all 20 grazing incidence samples, then go to each grazing incidence sample and at each do a grazing incidence alignment and then collect data at 0.12, 0.15, 0.18 degrees. And so you can batch out an entire collection of an entire group of grazing incidence samples. We also have a window that lets you load and run an arbitrary piece of code that you've written or that we've written. That's typically used in cases where there are accessory pieces of equipment that the user has brought in, and those need to be synchronized and coordinated with the data collection. So there is a fair amount of flexibility with our software as well. I'm going to talk briefly about analysis next. And here again, our most used software for analysis is still the APS Nika macros written by Jan Olavsky. And happy to give Jan Olavsky credit for his excellent work and demonstrate more evidence of the collaborative spirit between these facilities. Any user coming to Jan's beamline or who uses Nika will find these very familiar and available for use at 733. We are also engaged in doing some of our own software work. So at the ALS, we were the initiators for the Zycam project, which is a Python-based framework for multimodal X-ray data collection and analysis. Also, HipGSAX, which is high-performance computing software that lets you make a model of your sample, and then it'll predict the grazing incidence scattering from the model that you've specified. The ALS also very recently, created a computation group, and this group has started developing machine learning applications and started developing autonomous data collection capabilities where the beamline basically makes smart decisions to get you the desired results faster. And we're hoping for good things from that we can show in the coming years. So to close up, I want to say that users want data. Good data is king anytime they go to a beamline, but they also want a good experience. And we really try to deliver a good experience through easy to use software and stable equipment, communication and help getting your beam time set up, stage design assistance, training students and postdocs. And this is a number that makes me very happy about our beamline, is that in the last 4 years, 99.6% of our users rated their overall experience satisfied or very satisfied. Here are our contacts. Here's the very friendly and trustworthy Cheng Zhu and myself. And to obtain beam time at our beamline, first register as an ALS user at ALS Hub, and then use ALS Hub to submit a general user or rapid access proposal. The general user proposals are more appropriate for projects that will need multiple days of beam time every cycle. The rapid access are more appropriate for less complex beam times where you need, basically 1 day of beam time. And I'm going to turn it back over to Cheng now. He's going to talk to you about some of the unique strengths of the ALS in its soft X-ray and tender X-ray capabilities, and about the amazing things that you can achieve when you leverage resonant X-ray scattering. All right, so I will stop sharing, and Cheng, you can take over.
All right, thanks, Eric. I think Eric forgot to mention that 723 has been really the productivity champion of ALS for the past almost a decade now. So no, okay, well done. So now let me switch to medium rare, which is my favorite, the resin soft X-ray scattering. As all the experts here know that the small angle scattering it's great for many different applications, but when things become more complex, for example, you have a mixture of many different phases, then things are difficult to decouple. We are not dealing with dilute system every day anymore. We are not dealing with this highly ordered system either. So we're dealing with some system that has a mixture of many different things. So therefore, the contrast is becoming a critical thing that we need to get over. So the neutron community has been using the contrast matching method by replacing the hydrogen with deuterium to manipulate the scattering length density. The X-rays are limited by the material electron density, which is ultimately define the different contrast of different phases. So over the past decades also, we have been working on using the soft X-ray energy range to tune the X-ray energy to the core absorption levels of the atoms, mostly lossy element like carbon, oxygen, nitrogen, and where the incident photons excite the core level electrons into the unoccupied molecular orbital. So this process is elemental sensitive because different elements has different core binding energy of the core levels, but also sensitive to the chemical bond because where it's got excited to is closely related to the chemical environment that of interest. So basically, this effect was utilized in the hard X-ray regime, and it was called anomalous effect that has been quite successful. So for us, for the soft X part, we really kind of focus on the fine structure of the oscillations of the F prime, F double prime to get the subtle differences among the chemically similar materials. And all this, complex index is reflected in the material complex index refraction, which is a function of incident X-ray energies near the edge. And here is an example I'm showing here is a polystyrene and PMMA, two carbon-based polymer materials with different bond. One has a benzene ring, polystyrene, and one has a carbonyl group, which is both have one has 2 pi star resonance, but with a different chemistry, the resonance happens at different energies. So it's about 3 electron volt apart. One has 285, one at 288. So just by going to these 2 different energies, you can decouple these 2 materials, despite the fact that the electron density of these materials are relatively close. I think if you have a 2-phase system, that's really not a big issue. Conventional scattering will give you the picture you want. But when you get more than 1 phase, you have 3 polymers, for example, then you want to decouple the scattering contribution. I think this become very, very powerful. As reflected in this example here, we have an ABC tri-block polymer that's forming this complex phase, A and B and C phase, that by tuning the soft X-ray energies, that we actually tune in the scattering contribution of each component, and then we can go back and figure out which, how that phase is, contribute to the scattering, and then we can identify what the structure looks like unambiguously. So all this was done with the relatively new soft X-ray scattering beamline at ALS. It was actually constructed in 2010 after the successful commissioning of the beamline 733, which back then was led by Als Caching. We started, I was recruited to actually build this soft X-ray scattering beamline with a focus on the polymeric and soft materials. And so unlike the most small angle scattering beamline that you see, we don't have any hutch because we're running soft X-rays. And everything has to be running on vacuum. The large scattering cross-section of the soft X-ray, which gives a great benefit of contrast enhancement, also comes with a drawback. That is, the penetration is quite limited. So we are only able to working with relatively thin samples, it's really hard to implement the sample environment like in situ experiment. That has been the challenge, which has been the focus we have been working on over the past few years. And everything is done on the vacuum. And actually, as you can see, the diffraction angle is really not that small angle anymore. So in principle, we should call it small Q scattering because the large wavelengths, even at the large diffraction angle, the Q value achievable is comparable to what the typical small angle scattering experiment would be able to do. So we have, at this particular beamline, we have 150 eV to 1500 eV energy range that covers the low-Z elements, the carbon, nitrogen, oxygen, etc., as well as the transition metal L edges. The beam size is about 100 micron by 100 micron, so it's gives plenty of statistical information from the scattering experiment. Tony Young and Alex and I started in 2010, and David Kilcombe, which is now the beamline scientist at this beamline, he joined in 2016. Ever since the productivity has been ramping up, we are slowly, developed applications that become kind of common, a very common practice for material scientists to utilize this tool. I just want to give you a very, very overall picture of what resin soft X-ray scattering is. It really combines this cube space versus energy space. And give you both the spatial information from the typical small angle scattering experiment, adding the spectroscopy information into the picture. So you can see here, I'm using example of this early work done by Bridget Ingham on the casing molecules, where we have this casing colloidal molecules with carbon calcium phosphate nanoclusters inside. It's like the nanocomposite structure. By tuning the X-ray energies of the calcium resonance, you can see an envelope that's formed by the casing molecule overall size structure. But when you tune the energy near close to the calcium LH, L2, L3 absorption edges, you can see another scattering feature start to rise. That actually directly correlate to the correlation of the calcium distribution. So this is, I think this picture really captured the strength of the soft X-ray, resin soft X-ray scattering, is that when you tune to the different energy, you can selectively look at different phases. Although modeling and stuff is still complicated, but it's give you another dimension of information that you can leverage on. As an extension of that similar type of work, this is a very recent publication done by in collaboration with Ting Xu's group from UC Berkeley, where they are the world leading expert on this polymer nanoparticle composite materials, where they blend the nanoparticles and changing surface chemistry with a different tuned blocopolymer matrix, and by manipulate the chemistry, you can form different phases. Really this it's really complex in reality, and try to figure out the correlation, the phase diagram has been a challenge. Over here shows the TEM result of some of the material system they have. As you can see, you have to selectively staining the softer part to get the indication what's underlying matrix structure is, and then you can definitely see the polymer nanoparticle as this electron density is much higher than polymer. So basically, it's not a comprehensive picture. But then we move on to this resin soft X-ray scattering. Just to give you another look. Statistically, as you can see from here, for the different energies, you can see the very clear diffraction spot, okay, corresponding to the nanoparticle matrix. And you can see this amorphous halos that correspond to the form factor of either the nanoparticle or the core shell structure of the nanoparticle. But once you get into the details, then you can understand that you are sensitive, by tuning the energy, you're sensitive to either the polymer, in this case, is forming the lamella structure, that you have a very strong enhancement in this lateral direction, or you can sensitive to the core shell variation because of the nanoparticles surrounded by the polymer shell. So this is just showing that using the different energies, you can give you a clear differentiation of different phases in the system. And another capability that we hope we could enable is extend beyond the polymer system to a more general soft material basis. This is work shown in here is done at the Penn State University with Enrique Gomez and Esther Gomez group, and where we actually try to use the resin soft X-ray scattering to look at the very model system BSA proteins. The hope is that by tuning the photo energy where we're sensitive to carbon double bond to the carbon oxygen bond, that we will see a slight different shape of the small angle scattering profile that could represent the different envelope size of the proteins. As a result, that labeled here, the red part is the carbon double bond, the blue part is the carbon oxygen, and the gray part is the overall. So in comparison to the hard X-ray experiment, we were able to identify a different envelope size based on this chemical differences. And over the years, a majority of our publications are coming from a class of material, conjugate polymer blend, organic photovoltaics and organic LEDs. It happens to be the case that these thin films are of 100 nanometer in thickness, which is actually the sweet spot that we can run the scattering experiment in transmission geometry and get significant scattering contrast. So this is not achievable with hard X-ray because the cross-section is simply too small. The film is too thin. Therefore, we have to go through grazing incident geometry to enhance the interaction of the X-rays with the materials. But in the soft X-ray, the enhanced scattering cross-section as well as the tunable contrast give us a way that we can look at this complex structure, this heterogeneity, at different energies, you can see the spatial distribution of the nanophase separated bulk hydrogen junction structure. But one thing that in particular that is very unique to the soft X-ray is the sensitivity to the molecular bond orientation. So instead of having a diffraction profile like GWAX, that you can see the overall alignment of the molecules along the sample substrate, the soft X-ray is actually sensitive to the transition dipole moment of how these electrons are excited. Because, for example, you have a benzene ring sitting flat. If you have an incoming electromagnetic field vertical out of the plane, you can excite the electrons to the pi star orbital. But if you come in the other way, horizontal to the plane, you will not create such excitation. So this gives us a way to actually decouple the different molecular orientation together with the small angle scattering, and actually give us a unique perspective looking at the interface between the amorphous region and semi-crystalline region, because that will give us an overall different form factor. The effective form factor will be related to the incident X-ray beam polarization at resonance. At non-resonant condition, that's not visible, but at the resonant condition, if you come in horizontal polarization, you can see the form factor become like a rod vertically. If you come in horizontally, the form factor become a rod laying horizontally. So that is reflected in the anisotropy scattering, reflected in the profile. So this effect has been quite unique, and a lot of very exciting work came out after that. And then, my colleague Cheng has brought a very interesting material system, a liquid crystal system, which utilized this bond orientation sensitivity of the resonant soft X-rays to another new level. Ever since then, there has been a huge number of interest of studying this material, from very fancy faces formed by this twist band pneumatic liquid crystal to this almost blue face like liquid crystals. As you can tell, I'm not an expert in this area. If you want to learn more, please talk to Cheng regarding to the liquid crystal work and really utilize bond orientation sensitivity. Down the road, with a future coherent upgrade of the ALS, we will have the opportunity to see the fluctuation of the bond orientation. That is very exciting future to look forward to. Another class of materials that the soft X-ray is making a contribution to is actually in this semiconductor lithography application. This tremendous effort is led by the NIST group, Dean DeLongchamp, Joe Klein, and Sunday. They were developing this metrology tool using X-ray scattering for the decades. And the idea is actually you do a transmission X-ray experiment on the 2D grading structure, and then you collect the scattering profile as a function of incident angle, and you can reconstruct the Z information, so you get a three-dimensional profile of your grading structure. So this is has drawn quite some attention from the semiconductor chip manufacturing industry. And back then, there were a lot of work using the polymer-based direct self-assembly. For those thin films, only about 100 nanometer or 50 nanometer thick, the hard X-ray simply doesn't have enough cross-section. Therefore, the soft X-ray version of the same technique reveals a much enhanced intensity. Scattering really gives rise of the fine details of the 3D grading structure. And based on that, it was extended to different geometries. This is some early work we did using the Grazing incidence soft X-ray scattering on some EUV photoresist. The key here is that we are looking at the EUV photoresist in the latent stage. That means it's not developed. It's not washed off or anything. It's just exposed to the EUV mask exposure. And the only thing that is give us a scattering contrast is actually the chemical difference caused by the photoacid exposure. And then Dean's group actually has done some really tremendous work to push this technique to the extreme. They're actually using the polarized X-rays and running X-ray reflectometry, using the try to really get into the details about the molecular orientation along the film normal of this particular material systems. As you can see here, the S&P polarized reflectometry looks very different at different energies that really gives the fine details that you could not get otherwise of the depth profiling of the molecular orientation. So this is the typical sample holder that we run at soft X-ray beamline. As you can see, all the thin film samples deposits on the silicon nitride membrane. We can load up to like 70 samples at a time, so the user can run remotely or on-site. Over a 24-hour shift, you can go over all the samples that you can take home and get on a publication. And as I mentioned, the in situ experiment at the soft X-ray beamline is historically difficult due to this vacuum environment. Here are some early attempts that we try to sandwich some liquid with epoxy and liquid holders, and then we're adapting some existing in situ setup from other soft X-ray beamlines. And then I'll spend a little bit of time on the new development that we have. And in the meantime, we're adding some new capabilities such as in vacuum tensile testing and stuff, to complement to the hard X-ray in situ capabilities that you just heard from Eric. And this is all enabled with a strong user participation. I'm showing here Eric Michaud from Alliance Livermore Lab is testing his very fancy, I don't know what he's doing, stage. This is really engaging the user community to bring the new capabilities here. So as an example of this, the development over the past few years, we were supported to develop in situ sample liquid and gas cell with electrochemical capabilities inspired by the TEM sample holder. And we have a cell made by Protochips, which is a commercial TEM in situ cell holder provider, and we adapted the form factor of the sample tip, but adapted to the size and shape of the sample required for the soft X-ray scattering experiment, and we were able to get some really new experiment done. And you can, as you can see here, this customized sample chips allows the liquid and gas environment, as well as electrochemical connection that really enables the electrochemical type of characterization. As one of the first demonstration of this utilizing of the sample cell in collaboration with Brian Collins, group from WSU, this is some recent publication that we're using the liquid cell to study polymer micelle structure using the resonant scattering, and leveraging the tunable photon energies that we can really get the fine details of this core shell structure of this polymer micelles. And the data analysis, again, I will give credit to Jan Levasky from APS. We were actually leveraging the very strong program, NICA program, and in collaboration with Brian Collins and Washington State, we developed a user plugin that adapt to the soft X-ray scattering data, because as you can tell, every scattering profile was collected at different energy. Therefore, the wavelengths and the energy will be quite different. So the input is slightly different from the typical small scattering that you would do. Young has been tremendous help to help us to implement this plugin and made it available to the users. Let's see. Okay, in the meantime, as I mentioned, we're really leveraging the strong user community support. We have this NSF consortium that actually building a customized chamber that's allow us to bring commercial TEM sample holders directly to the soft X-ray scattering setup. David Kilcone is actually the main scientist actually leading the development of this particular setup. The ultimate goal we have is actually really enable the multimodality that offers by both electrons and X-rays, that we can leverage the different probes on the same sample eventually at the same time, that give us this correlated information about the material system, with especially the in situ characterization, which hope to bring it to a new level. So that's about the soft X-ray scattering. If you have any questions, please contact myself or David Kilcone. But then I haven't finished yet. Sorry. I want to briefly mention the new development that we're working on, and the 10 X-ray scattering is a new capability that we are trying to build upon. And Gregory Su is actually leading the scientific development. We already have the equipment that we're going to leverage the existing setup to build a tender beamline. And as an early example of this application, we were using this tender scattering to study polysulfuric membrane for the proton conducting work. Meanwhile, ALS is moving towards the coherent scattering, coherent facility, and the XPCS is definitely, that's why we're merging the scattering group leading by Sujoy Roy. So we get strategically, we want to extend XPCS to soft materials as well. And just last slides about the ALS upgrade. As you can see, the dome building here, the historical building, the ALS will be upgraded and will be conserve the dome structure and a brand new ring with multi-band achromat ring that will bring the beam profile from here currently to here. That will tremendously increase the coherent flux of the ALS, make it one of the brightest of the synchrotrons. And we are at the sketching group, we are in charge of building a new tender beamline as one of the two beamlines that at ALSU that will offer the tremendous coherent X-ray scattering capability in the tender X-ray range. We're really looking forward to that. Before I finish, I really want to squeeze in an advertisement. I'm looking for a postdoc on sustainable polymers. If you have any interested candidates, please have them contact me. Go to this website for this postdoc will be working on in situ soft texture characterization of the chemical transformation of polymers. So with that, I would like to thank Eric, thank the organizer again. If you have any questions, I have time, I'm happy to answer them.